Imagine you are walking through a sunlit meadow on a crisp, late summer morning. The grass is tall, it's brushing right up against your knees, and the ground is saturated with a really heavy dew.
Oh, that's the perfect condition for them.
Right. And as you're moving through this field, you stumble upon something that looks completely out of place. It's almost jarring in its geometry.
Mhm.
You see this towering umbrella-like structure standing nearly 40 centimeters tall.
Which is, what, over 15 inches?
Yeah, over 15 inches, proudly erected in a perfect, almost mathematically precise circle of identical towering umbrellas.
It's quite a sight.
It really is. And
Right.
you reach out, you touch the stem, and you notice it has this distinct repeating pattern that looks uncannily like the scales of a snake.
The snake skin's tight. Yeah.
Exactly. You are looking at Macrolepiota procera, which most people know as the parasol mushroom. And today, you and I are taking a deep dive into an organism that is fundamentally going to change how you look at the natural world.
It truly is a remarkable organism to encounter in the wild. I mean, when you see a full flush of them standing in that perfect ring, it feels like something plucked straight out of a medieval fairy tale.
Oh, totally.
But the reality of what this organism is executing biologically, both beneath the surface of the soil and right there in the air around the cap, it's far more complex and, frankly, far stranger than any of the folklore.
And that's exactly why we are diving into this today. I mean, we've pulled together a massive stack of sources for this deep dive. We're looking at ecological studies, biochemical analyses, historical folklore records, and, mycological field guides.
Right, a really multidisciplinary approach.
Because we are looking at a species that defies almost every casual assumption you might have about fungi. We are talking about an organism that acts as a highly efficient environmental heavy metal filter. It's an active manipulator of fluid dynamics, and it even produces highly complex mammalian neurotransmitters.
It's basically a biological marvel hiding in plain sight in pastures all across the world.
Exactly.
And, the depth of its ecological integration is staggering. When you synthesize the data across all these fields, you realize the parasol mushroom is basically a masterclass in evolutionary bioengineering.
Which is what we're going to unpack today.
Right. Our objective is to break down the exact mechanisms of these processes. We need to understand the structural physics that allow it to stand that tall, the chemical pathways it uses to alter the soil, and obviously the profound pharmacological implications of the compounds it synthesizes.
Yeah, we are going to get into some heavy chemistry and localized weather manipulation later. But before we do that, I think we really need to ground ourselves in the sheer physical architecture of this mushroom.
Oh, absolutely. The structure is key.
Because the biomechanics of Macrolepiota procera are an absolute feat of natural engineering. So let's trace how this thing actually builds itself. It doesn't just, pop out of the ground fully formed.
No, not at all.
It begins in this juvenile state that mycologists refer to as the marginate phase, or the drumstick phase.
Precisely. So in this initial phase, the cap is spherical or ovoid, and it's tightly closed against the stem. Visually, it really does resemble a drumstick just resting in the grass.
And that shape isn't just an accident, right?
No, this closed architecture is highly intentional. It creates a hermetically sealed, high-humidity microenvironment inside. And that's guarded by a really tough structural tissue called the partial veil.
Okay, so it's acting like a protective shield.
Exactly. This sealed chamber allows the delicate spore-bearing gills to fully differentiate and develop. And it does this without being exposed to external desiccation or UV radiation or even predation from insects.
And then comes the expansion phase, which I just find physically fascinating because it's not growing the way an animal or a plant typically grows, right?
Right, it's entirely different.
It's not slowly adding billions of new cells to build a wider umbrella over a period of weeks. It rapidly hydrates. It's essentially using hydraulic pressure, pumping water into its existing cellular matrix to expand the cap outward at a dramatic pace.
Yes, the speed is incredible.
But there's a structural problem because the dark, rigid outer skin of the cap, the cuticle, it can't expand at the same rate as the highly elastic, white, fleshy material underneath it. So something has to give.
Yes, the biomechanical tension reaches a critical threshold. The differential expansion between that hydrating interior and the rigid exterior forces the cuticle to violently fracture.
It just rips apart.
It literally tears apart across the surface of the expanding cap. And that is exactly what creates those characteristic, beautiful concentric brown scales. The scales are just the shattered remnants of the original juvenile cuticle resting on top of the newly expanded pale cap.
Okay, let's unpack this. So it's like an inflating balloon covered in a layer of dried clay. As the balloon expands, the clay shatters into a puzzle piece pattern.
That's a highly accurate mechanical visualization. Yeah, it's a very efficient deployment strategy.
Because it doesn't have to build new skin.
Exactly. It allows for the rapid unfurling of the reproductive surface without the immense metabolic burden of synthesizing entirely new elastic cuticle tissue in just a matter of hours. And as that cap flattens out, stretching up to 30 or even 40 centimeters across, it retains a distinct structural node perfectly in the center, the umbo.
Right, the umbo. Visually, it's this blunt, dark bump sitting right in the middle of the parasol.
And its function is entirely structural. I mean, consider the sheer physical stress of supporting a 40-centimeter wide, water-dense cantilevered umbrella on a single central pillar.
Especially out in an open meadow.
Right, especially when exposed to ambient wind. The bending moments and the sheer stresses at that point of attachment are immense. So the umbo acts as a structural pivot point and a load-distributing hub.
That makes perfect sense.
It provides the necessary localized tissue density to safely transfer the weight and the wind load of that massive cap directly down the vertical axis of the stipe.
Hang on, I need to stop you there because the stipe itself is where the structural engineering gets really, truly hard to believe.
It really is wild.
We're talking about a stem that can be up to 40 centimeters tall, but only 1 to 3 centimeters thick. And the defining characteristic of it is that it is fistulous.
Right, meaning it is completely, entirely hollow inside.
Exactly. It's a hollow tube carrying a massive, heavy, wet umbrella. How on earth does it not snap instantly the moment a strong gust of wind hits that cap?
Well, it is a classic optimization problem in biomechanics. The hollow core is actually a highly calculated evolutionary trade-off regarding resource allocation.
How so?
If the mycelial network were to build a solid, dense stipe that was 40 centimeters tall and 3 centimeters thick, the metabolic cost would be massive.
Just too much material.
Exactly. The sheer amount of carbon, nitrogen, and energy required to synthesize that much dense chitin would be exorbitant. It would severely limit the number of fruiting bodies the network could produce. So it opts for a hollow cylinder.
But a hollow cylinder made of soft fungal tissue should just buckle, right?
It would if it were uniform, but the walls of that hollow cylinder are packed with tightly woven, highly oriented longitudinal hyphal fibers.
Okay, so it's reinforced.
Heavily. In structural engineering, a hollow tube with dense walls offers the highest possible moment of inertia, which is the maximum resistance to bending and wind shear relative to its mass.
So when the wind hits the cap.
When the wind exerts lateral force on the cap, that force is transferred down the stipe. The longitudinal hyphae on the windward side of the tube resist massive tension, while the fibers on the leeward side resist massive compression.
Oh, wow.
By keeping the center hollow, the mushroom minimizes its metabolic building costs while maximizing its structural resilience against wind shear.
Okay, so it's employing the exact same mechanical principles as a modern skyscraper core or, a bamboo shoot. But it's utilizing fungal chitin instead of steel or cellulose. That is just brilliant.
It really is.
And while we're talking about the stipe, I have to bring up the ring, the annulus. When that juvenile drumstick cap expands and the partial veil rips away, the remnants of that veil are left hanging on the stem.
Right, the classic mushroom ring.
But in most mushrooms, that ring is just stuck there. On the parasol, the ring is thick, it's double-edged, and it is completely detached from the stem. You can literally slide it up and down like a ring on a finger.
Yes, the movable annulus is a prime example of localized, highly controlled enzymatic degradation.
Meaning it chemically cuts itself free.
Exactly. During the expansion phase, Macrolepiota procera secretes highly specific allolytic enzymes, likely targeted chitinases and glucanases, that dissolve the cellular bonds exactly at the point where the veil tissue attaches to the stipe tissue.
That's incredibly precise.
It cleaves the connection perfectly without degrading the structural integrity of the stipe itself.
Which obviously is incredibly helpful for foragers trying to identify it in the field. But from an evolutionary perspective, why go through all this trouble?
What do you mean?
Well, why build a 40-centimeter tall hollow tower with a massive heavy cap and a complex enzymatic ring system? That high aspect ratio seems like a massive, unnecessary risk just to lift your gills off the ground.
It is a risk. But what's fascinating here is that extreme height is the fundamental requirement for a highly sophisticated, proactive, reproductive strategy.
Okay, so it's all about reproduction.
Always. Fungi exist to disperse spores. And if you were trying to disperse spores in a dense meadow, Being tall isn't just an aesthetic flex, it is an aerodynamic necessity.
Which completely flips the script on how we assume mushrooms operate. Because the old assumption, and frankly what I was taught in biology, was that spore dispersal is entirely passive.
Right, that was the standard model.
A gilled mushroom drops its spores out of the cap, they fall like dust, and the mushroom just crosses its fingers hoping a random breeze will catch them before they hit the dirt.
That was the prevailing model for decades. But fluid dynamic studies, utilizing advanced imaging techniques, have revealed that Macrolepiota procera and several other large basidiomyces do not wait for ambient weather.
They don't?
No. They actively manipulate the atmosphere around them. They generate their own localized convective currents.
Okay, I am still having a hard time picturing this. You're telling me a mushroom generates weather. How is that physically possible? And how did physicists even prove this?
Well, it comes down to basic thermodynamics and highly specialized imaging. So the underside of that massive 40-centimeter cap is lined with thousands of densely packed gills, right?
Right.
Which represents a massive, highly hydrated surface area. Water is constantly evaporating from the hymenium, the spore-bearing tissue on those gills.
Okay.
As water transitions from a liquid in the fungal tissue to a vapor in the air, it absorbs latent heat from the immediate surroundings. This process of evaporative cooling significantly drops the temperature of the air layer directly beneath the umbrella of the cap.
Oh, I see. And colder air is denser, so it sinks.
Exactly. You have a dense mass of cooled air that begins to sink vertically down the stipe toward the ground. But nature abhors a vacuum.
Right, so new air has to replace it.
As that central column of cold air drops, warmer, slightly less dense air from the surrounding environment is drawn inward and upward over the top of the cap, curling around the edges to replace the sinking air.
Wow.
This creates a continuous, localized convective cell, essentially a toroidal vortex of airflow, driven entirely by the mushroom's evaporation rate.
So it's literally functioning as a biological evaporative cooler, driving a microcurrent of air. But, I mean, if I crawl under this mushroom in a field, am I actually going to feel a breeze on my face?
No, you wouldn't feel it on your skin. The velocities are just too subtle for human mechanoreceptors.
Okay, so how do we know it's there?
Researchers prove this using particle image velocimetry, or PIV. They introduce microscopic laser-illuminated aerosols into the air around the mushroom and track the movement of those particles with high-speed cameras.
That's amazing.
The PIV data proves these convective cells generate continuous airflows traveling at speeds of several centimeters per second.
Now, several centimeters per second sounds trivial to us, but the spores this mushroom is dropping are less than 10 micrometers in size, right?
Right. They weigh practically nothing.
So a draft of a few centimeters per second is essentially a hurricane-force wind for a spore. It's more than enough to grab those spores as they fall out of the gills and sweep them horizontally, pushing them out from underneath the protective umbrella of the cap.
Precisely. And this is where the towering 40-centimeter stipe becomes absolutely vital. If the parasol mushroom only grew 10 centimeters tall, down inside the dense grass of the meadow, it would be trapped in the boundary layer.
The boundary layer being the zone where the grass creates friction and completely blocks the ambient wind, leaving just stagnant dead air.
Exactly. If it drops spores down in the boundary layer, the convective current might push them a few inches, but they would eventually just fall to the ground directly beneath the parent.
Which defeats the purpose.
Entirely. They would germinate and immediately compete with their own parent network for the exact same localized soil nutrients. It's an evolutionary dead end.
But by building that massive hollow tower, it punches right through the boundary layer.
Yes, it elevates the cap out of the wind shadow of the tall grass and up into the turbulent zone of the atmosphere, where ambient wind speeds are significantly higher.
So it's a two-stage process.
Correct. The mushroom uses its self-generated convective engine to horizontally push the spores out from under the cap, and the moment they clear the edge of the umbrella, the high-altitude ambient winds of the turbulent zone rip them away.
That is just staggering. On a completely still, windless August morning, when not a single blade of grass is twitching, this mushroom is quietly generating an invisible vortex of air, actively flinging millions of spores out across the landscape to travel potentially kilometers away.
It is proactive environmental engineering at a microfluidic level. It's incredible.
It really is.
But the story gets even more complex when we look at what happens when those spores finally land. Because a successful spore doesn't just sprout a cute new little mushroom.
Right.
It begins the construction of a subterranean network that fundamentally alters the biochemistry of the soil. And this brings us to the ecological phenomenon of the fairy ring.
Yes, the fairy ring. To really understand what's happening underground, we have to look at the specific ecological role of Macrolepiota procera. It is a saprotrophic fungus. But to be clear, it's not breaking down wood.
No.
You aren't going to see a parasol mushroom growing out of a rotting oak log in the forest. It specifically targets complex plant debris in the soil, like dead grass, leaf litter, decaying root systems.
Correct. It is a terrestrial, litter-decomposing saprotroph. When a spore lands in a suitable pasture, it germinates and begins pushing out thread-like hyphae, forming a mycelial network.
And then it starts eating.
Yes, this mycelium secretes a highly potent cocktail of extracellular enzymes like lignases and cellulases into the surrounding soil. These enzymes break down the rigid, complex polymers of dead plant matter into simple, soluble molecules that the fungus can absorb for carbon and energy.
But this enzymatic mining operation is incredibly intensive, right?
Extremely intensive, meaning it rapidly depletes all the available food in that specific starting location.
So it has to move.
Exactly. As the mycelium consumes the available substrate at the point of origin, the localized food source runs out. The central, oldest part of the network slowly starves and dies off. But the active leading edge of the mycelium continues to grow outward radially in all directions, constantly seeking fresh organic matter.
Which creates an expanding, living circle of active fungal tissue moving outward through the soil like a slow-motion subterranean ripple.
That's a great way to picture it.
And when the environmental triggers align, usually a drop in temperature and a heavy rain, that active outer ring of mycelium pools its resources and pushes up fruiting bodies. And the mushrooms emerge in a massive, perfect circle.
And these mycelial waves can reach just astonishing proportions over time. The outward expansion rate is relatively consistent, often 10 to 30 centimeters a year, depending on soil conditions.
So they get huge.
Some related species form rings that literally defy human lifespans.
Right. Our sources highlight a famous ring in France. Now, to be perfectly accurate to the source material, the specific species in that study is Infundibulus geotropa, the trooping funnel mushroom. But it perfectly illustrates the exact same saprotrophic ring mechanics the parasol uses.
Yes, the mechanics are identical.
This ring in France is over 300 meters wide. That's 3 entire football fields across. Based on the radial growth rate, ecologists estimate that single, unbroken mycelial network is over 700 years old.
700 years.
It has been slowly expanding outward through that field since the Middle Ages.
The sheer temporal scale is humbling. But what's really important is how this advancing fungal wave drastically alters the soil chemistry and consequently the plant life above it.
Okay, let's get into the chemistry of the ring.
As the Macrolepiota mycelium breaks down complex organic matter, it is also liberating vast amounts of nitrogen that was previously locked away in the dead plant tissue.
Through mineralization.
Exactly. Through a process called mineralization, it converts organic nitrogen into highly bioavailable forms, like simple nitrates and ammonia.
So it's essentially manufacturing high-grade fertilizer underground.
Precisely. And this localized flush of bioavailable nitrogen completely supercharges the grass growing directly above the active leading edge of the ring.
I've actually seen this.
You have. This is why, in a seemingly uniform green meadow, you will often spot a perfect geometric ring of exceptionally lush, dark green, vigorously growing grass, even weeks before the mushrooms themselves emerge. The grass is exploiting the nitrogen exhaust of the fungal engine.
But this interaction isn't always a purely beneficial nitrogen feast for the grass, is it? Because the literature points out that these fairy rings can also create what are known as necrotic zones.
Yes, there is a distinct ecological duality here, and it's largely dependent on moisture levels.
How does that work?
In dry conditions, the active edge of the mycelial ring becomes incredibly dense. The fungal threads weave into an almost impenetrable mat just below the soil surface. Furthermore, the mycelium secretes hydrophobins. These are specific proteins that coat the hyphae and render the entire mat highly hydrophobic, meaning it aggressively repels liquid water.
So it creates a literal waterproof shield just under the grass.
Exactly. When it rains, the water hits that hydrophobic fungal mat and simply runs off. It cannot penetrate down to the root systems of the grass growing directly above it.
Oh, wow. So the grass just dies.
Consequently, the grass in that specific circular zone suffers acute drought stress and dies, creating a perfectly defined ring of dead, yellowed, scorched-looking earth right in the middle of a green field.
So you have this invisible underground organism that randomly creates either rings of hyper-fertilized lush grass or rings of completely dead, scorched earth.
And it's doing all of this while managing a highly complex dialogue with soil bacteria.
Right. This brings up the concept of the mycorrhizasphere. And I really want to clarify this because when people hear mycorrhizal, they usually think of a fungus that directly plugs into the roots of a living tree to swap sugars for minerals.
The classic symbiotic relationship.
Yeah, but the parasol is a saprotroph. It eats dead things. It doesn't plug into living root.
It does not form direct symbiotic root associations like an ectomycorrhizal amanita or boletus. However, it absolutely manipulates the microbial community in the soil volume surrounding its hyphae.
The hyphosphere.
Yes, this zone of influence is called the hyphosphere, or more broadly within plant-soil interactions, the mycorrhizasphere. The parasol is constantly secreting a complex array of chemical, exudates simple sugars, organic acids, and volatile organic compounds directly into the soil matrix immediately surrounding its network.
And it's deliberately doing this to recruit very specific bacterial species. Our sources highlight Panabacillus validus as a key partner.
A vital partner, yes.
So to make sure I understand the mechanism here, the fungus is sitting on a mountain of carbon it extracted from dead grass. The bacteria need that carbon, but they can't break down the dead grass themselves, so the fungus leaks simple sugars to attract the bacteria. But what exactly is the fungus getting out of this exchange?
It's a highly transactional tripartite interaction. The fungus provides the easily digestible carbon. In return, the recruited Panabacillus validus colonies provide several critical services.
Like what?
First, they produce specific vitamins and growth factors the mycelium cannot synthesize efficiently on its own. Second, they utilize their own specialized enzymatic pathways to mobilize recalcitrant soil minerals.
Like breaking down rocks.
Essentially, yes, like bound phosphorus, making them water-soluble and accessible to the fungal hyphae. And perhaps most importantly, these bacterial colonies act as a biological defense system.
Oh, against other microbes.
They secrete potent antimicrobial compounds that protect the vulnerable growing tips of the fungal network from aggressive parasitic soil pathogens.
It really is a subterranean economy. So you're saying the dead plant matter is the raw resource, the fungal network is the extraction machinery, and the bacterial workforce handles the refining and the security.
That's a brilliant way to phrase it.
It is this vast, invisible, highly communicative web of biological trade.
It is. And it's entirely invisible to us on the surface until that precise moment when the fruiting bodies emerge.
Which is when things get really weird historically.
Right. And this is where a critical shift in perspective is required to understand the cultural impact of this organism. Imagine being an agrarian European in the 14th century.
Okay, I'm a medieval farmer.
You do not have an electron microscope. You have no concept of nitrogen mineralization, hydrophobic mycelial mats, or Panabacillus validus. All you see is a perfectly circular ring of scorched, dead grass suddenly appearing in your pristine pasture overnight.
And the very next morning, an organized ring of giant, towering, scaly umbrellas has violently erupted from that dead earth.
Right. You aren't going to look at that and think, fascinating saprotrophic radial expansion.
Definitely not.
You are going to think you are looking at dark magic. You are going to think your land has been cursed.
And that reaction birthed some of the most pervasive, intense, and frankly terrifying folklore in human history. Let's talk about the legends because they are wild.
The psychological terror associated with these rings is incredibly consistent across almost all European cultures. They weren't viewed as natural curiosities, they were designated hazard zones.
What did the French call them?
In France, they were known as ronds de sorcière, or sorcerer's rings. The prevailing superstition held that these massive circles were guarded by giant, malevolent, bug-eyed toads that would unleash curses on any farmer who dared to step inside the boundary or disturb the mushrooms.
Giant toads. And in Germany, the associations were similarly dark. They called them Hexenringe, or witches' rings.
Yes.
The belief was that these perfect circles marked the exact locations where covens of witches danced under the moonlight, specifically on Walpurgis night, stamping the grass dead as they communed with demonic forces.
The Dutch folklore offers a fascinating variation, too. Their superstition claimed that the circular necrotic zones in the grass were the exact spots where the devil himself had rested his massive burning milk churn upon the earth.
A burning milk churn? That's so specific.
Meanwhile, in the Tyrol region of the Alps, the cultural explanation shifted from witches to cryptids. The local legends attributed the scorched rings to the fiery tails of flying
I
dragons.
love the dragon theory.
They believed that once a dragon touched down and its tail scorched the earth in a perfect circle, the land was poisoned, and nothing but toxic toadstools could grow there for 7 years.
I just love that one because it shows how perfectly the folklore was trying to explain the physical evidence. I mean, we know the ring of dead grass is caused by a hydrophobic fungal mat repelling water.
Right.
But to a pre-scientific mind, the blast radius of a dragon's tail landing in a field is a perfectly logical deduction for why a perfect circle of grass looks like it was flash fried.
Exactly. Folklore is essentially early humanity's attempt to map ecological anomalies and establish behavioral protocols around them. We see a perfect circle in nature, which is inherently rare and visually jarring. And our pattern-seeking brains just demand a narrative explanation.
And no culture leaned into that narrative harder than the Celts and the Scandinavians, who popularized the concept of the fairy ring.
Ah, yes.
Their tradition blamed the rings on the midnight revelries of elves or fairies. The fairies would dance in a frenzied circle under the full moon, their fast-moving feet burning the grass, and the mushrooms would magically spring up the next morning exactly where they had stepped.
It's a very poetic image.
Even Shakespeare documented this cultural obsession. In A Midsummer Night's Dream, he writes of the fairies doing their orbs upon the green. And in The Tempest, he talks about the unseen entities that, by moonshine, do the green sour ringlets make, whose midnight pastime is creating mushrooms.
But we need to remember these weren't whimsical, friendly fairies like we picture in modern cartoons.
No, not at all.
They were dangerous, chaotic entities. And interacting with their rings was governed by a strict, highly consequential set of rules. You couldn't just casually investigate a fairy ring in your pasture.
It was dangerous ground.
If a farmer accidentally ran a plow through one, the oral tradition held that he would anger the inhabitants, his livestock would sicken, and his crops would blight.
The rules of the ring are intense. Our sources detail the exact protocol you were supposed to follow.
Oh, let's hear the protocol.
If you absolutely had to investigate a fairy ring, Celtic legend mandated that you must run around the outside perimeter exactly 9 times.
9 times.
Furthermore, this had to be executed under the light of a full moon, and you had to travel clockwise in the direction of the sun. If you executed that perfectly, the veil would thin, and you would be granted the ability to hear the fairies reveling underground.
But there's a catch, right?
A massive hazard warning. If you miscounted and ran around the ring a 10th time, it was considered immediately fatal. You belong to the fairies now.
It's terrifying. There were deeply ingrained protective countermeasures as well. Some superstitions stated that if you had to walk past a ring, turning your hat backward could confuse the fairies' magic and prevent them from ensnaring you.
Turning your hat backward.
Because being pulled inside the boundary was the ultimate terror. The legends warned that any mortal who stepped foot inside the ring would become invisible to the mortal world, instantly trapped in the fairy realm. And the punishment for intruding was forced participation in their dance.
You'd be forced to dance to the point of absolute madness, total exhaustion, or death. And even if you were miraculously rescued, which supposedly required an outsider anchoring themselves with an iron tool or waiting exactly a year and a day to pull you out, the outcome was horrific.
Tragic outcomes, yeah.
There are Welsh tales of people being yanked out of a fairy ring only to instantly crumble to dust on the spot, because what felt like a few hours of dancing to them was actually centuries passing in the real world.
The time dilation element is so common.
So when we strip away the magic, what are we actually looking at here? Why did human psychology universally look at a circular fungal growth pattern and immediately associate it with time dilation, forced dancing, neurological madness, and death?
Well, this is where ecological hazard mapping becomes really evident. While the parasol mushroom itself is edible, the fairy ring phenomenon is not exclusive to Macrolepiota procera.
Right, lots of mushrooms grow in rings.
Many other species form massive rings, and several of them, like Clitocide dealbata, the sweating mushroom, or certain Amanita species, are highly toxic, containing severe neurological poisons. If a foraging human, or a farmer's livestock, grazed on mushrooms from a fairy ring and subsequently experienced severe muscarine poisoning, muscle intoxication, or ergot-like hallucinations.
They wouldn't know it was poison.
Exactly. The oral tradition would encode that physiological trauma into a supernatural story.
That makes total sense. The madness of being forced to dance is a cultural memory of severe neurological poisoning and muscle spasms. The time dilation is a recounting of the hallucinatory dissociative state of the victim.
Precisely. If we connect this to the bigger picture, the folklore acts as an incredibly effective multi-generational hazard warning. The fairy ring becomes a designated, culturally enforced do not touch zone.
Even if some of the effects were positive.
Although, interestingly, the ecological benefits of the nitrogen flush weren't entirely ignored by the folklore either.
Really?
Yeah, the Athenian oracle recorded a localized belief that if you built a house directly upon a fairy ring, it would guarantee prosperity and fertility for the inhabitants.
Probably because any vegetable garden you planted over that bioavailable nitrogen sink was going to absolutely explode with massive yields, so they recognized the fertility aspect too.
They observed the results, even if they didn't know the mechanism.
But while our medieval ancestors were terrified of the magical curses of the ring, modern science has revealed that the parasol mushroom actually does harbor some incredibly potent and highly dangerous chemical secrets. We need to transition from the folklore to the physical biochemistry.
The chemistry is where it gets truly wild.
We need to talk about exactly what this massive underground mycelial network is pulling out of the soil.
This is where the sheer efficiency of its saprotrophic nature becomes a double-edged sword. Macrolepiota procera is recognized by environmental toxicologists as a hyper-accumulator.
What does that mean in practice?
Because its mycelial network is so dense, and its enzymatic breakdown of soil matter is so aggressive, it acts as a massive biological vacuum, and it doesn't discriminate well.
It just sucks up everything.
Alongside the essential nitrogen and carbon, it actively draws up dangerous heavy metals and even radioactive isotopes from the soil, funneling them up into the fruiting body.
So it's basically a radioactive fungal sponge. The numbers in the ecological studies are just deeply concerning, especially regarding mercury.
And mercury data is shocking.
The studies looked at parasol mushrooms growing in pristine, uncontaminated European forests miles away from any industrial sites. The scientists measured the mercury concentration in the caps of the mushrooms at 6.29 milligrams per kilogram of dry weight.
That is extremely high.
To understand how crazy that is, the soil directly beneath that mushroom only registered 0.02 milligrams per kilogram. It is concentrating the ambient mercury by staggering orders of magnitude.
Yes, the bioaccumulation factor, or BAF, is exceptionally high. Fungi utilize specific metal-binding proteins, similar to metallothioneins, which actively sequester these elements, and it goes far beyond mercury.
What else is it absorbing?
The literature shows it hyperaccumulates cadmium, which is a highly toxic heavy metal that causes severe renal failure in humans. It also bioaccumulates silver, showing BAF values ranging from 67 to 420.
Wow.
This means the mushroom contains up to 400 times more silver than the substrate it is actually growing in.
And the most alarming data point for anyone thinking about tossing this in a frying pan is the radioactivity.
Yes, the isotopes.
The studies confirm it bioaccumulates naturally occurring radioactive isotopes, specifically lead-210 and polonium-210.
Polonium-210 is notoriously dangerous.
It's an incredibly lethal alpha emitter. It's the exact same isotope used in high-profile espionage assassinations like Alexander Litvinenko. And this beautiful tall meadow mushroom is just quietly vacuuming it up from the natural background radiation of the Earth and storing it in its umbrella.
It is a critical hazard. The highest concentrations of these toxins, heavy metals, and isotopes are almost exclusively deposited in the cap, specifically within the hymenophore, the gill tissue. The holostype generally registers much lower concentrations.
Okay, so the cap is the danger zone.
But this intense hyperaccumulating behavior has actually turned the parasol into a crucial tool for environmental scientists. By foraging and testing these mushrooms, radioecologists can effectively map the background heavy metal contamination and isotope levels of an entire forest ecosystem. The mushroom does the sampling for them.
Here is the massive paradox, though. Here's where it gets really interesting. You have an organism that is undeniably a toxic, radioactive, heavy metal sponge. But at the exact same time, deep within its cellular walls, it possesses a pharmacological profile that reads like a cutting-edge miracle drug.
It is a fascinating dichotomy.
The biochemical duality is almost hard to process. Let's look at the medicinal side, starting with MPCPS.
Right. MPCPS refers to a highly specific, water-extractable polysaccharide fraction found in the fruiting body. It's primarily composed of complex beta-glucans. In rigorous pharmacological studies, these specific beta-glucans have been shown to act as highly potent biological response modifiers, or BRMs.
Okay, a biological response modifier. To be clear, that means it doesn't function like penicillin or chemotherapy drug that travels through your blood to directly attack and kill a pathogen or a cancer cell.
Correct. It does not exhibit direct cytotoxicity. Instead, it interfaces directly with the human immune system.
How does it do that?
When ingested, these specific fungal beta-glucans are recognized by pattern recognition receptors, specifically the dectin-1 receptors, on the surface of human macrophages and T cells.
Okay, white blood cells.
This interaction essentially primes or wakes up the white blood cells. It enhances their phagocytic activity and their production of cytokines, vastly improving the immune system's baseline ability to recognize and destroy tumors or invading pathogens on its own.
That's incredible.
Furthermore, researchers have isolated a highly complex, unique glycan from the parasol, aptly named Lepiotan, which has demonstrated very specific, targeted anti-tumor activities in laboratory models.
So wait, it's storing toxic heavy metals that cause cellular damage while simultaneously synthesizing complex beta-glucans that teach your immune system how to fight cancer?
Yes.
But the biochemistry gets even stranger when we look at neurology, because the absolute most surprising finding in these papers revolves around mammalian brain chemistry.
The neurotransmitter data.
When researchers analyzed fresh specimens of the parasol mushroom, they found incredibly high concentrations of a compound called 5-hydroxytryptophan, or 5-HTP. They measured it at 22.94 milligrams per 100 grams of dry weight.
Which is a very significant yield.
Now, anyone who has browsed the supplement aisle at a pharmacy looking for mood support or sleep aids knows exactly what 5-HTP is. It is the direct metabolic precursor to serotonin.
Yes. Serotonin is a fundamental neurotransmitter in the human central nervous system. It heavily regulates mood, appetite, thermal regulation, and sleep cycles. And the parasol mushroom doesn't stop at 5-HTP.
There's more.
Advanced chromatography has confirmed it also synthesizes measurable amounts of melatonin, the primary hormone regulating circadian rhythms, as well as tryptamine.
That's just wild.
To find these highly specific neuroactive indole derivatives, compounds we strictly associate with mammalian brains, in such massive concentrations in a saprotrophic meadow-fungus is biologically astounding.
Which begs the obvious question, why? Why does a mushroom need the chemical building blocks of human happiness? It's not trying to cure a badger's depression. What evolutionary purpose does a fungus have for synthesizing 22 milligrams of 5-HTP?
This raises an important question, and it's a phenomenal one that touches on the deep evolutionary conservation of these molecular pathways. Fungi obviously do not possess nervous systems.
Obviously.
They're synthesizing these complex indole derivatives for entirely different, likely protective cellular reasons. Fungi growing in open meadows are subjected to massive environmental stress. Intense UV radiation from direct sunlight, rapid temperature fluctuations, and desiccation.
They're just sitting out in the open.
Right. These environmental factors generate massive amounts of reactive oxygen species, leading to severe oxidative stress that can damage fungal DNA.
Ah, so it's using them as a defense mechanism.
Precisely. Melatonin, for example, is not a sleep hormone to a fungus. It is a phenomenally potent, broad-spectrum antioxidant and a highly effective free radical scavenger.
Oh, I see.
The mushroom synthesizes these indole pathways as an internal cellular defense system against UV damage and oxidative stress. It is essentially manufacturing its own highly advanced internal cellular sunscreen.
Wow.
The fact that these exact same molecules fit perfectly into the receptor pathways of the human nervous system is an extraordinary evolutionary coincidence.
It's an evolutionary coincidence that humans would absolutely love to exploit, but that brings us right back to the paradox. How do we balance this?
That's a tricky balance.
You have a mushroom that represents a massive therapeutic potential as a functional food for depression, insomnia, and immune support. But if you eat it to boost your serotonin, you are simultaneously ingesting a microdose of cadmium, mercury, and polonium-210.
Yes.
The biological cost-benefit analysis of eating a wild parasol is incredibly murky.
It is a significant public health consideration, and it transitions us perfectly into the final logistical challenge, the intersection of foraging and cultivation. Because despite the heavy metal risks, which, frankly, the vast majority of traditional foragers are completely unaware of, the parasol mushroom remains highly prized in culinary circles across Europe.
Oh, it is considered an absolute choice edible. Chefs love it. The cap, specifically, is a delicacy. When it is harvested young, While still partially closed or just after it flattens out, the flesh is incredibly tender.
Very aromatic.
It has a mild, nutty, highly aromatic flavor profile. A very common traditional preparation is to take the entire massive cap, bread it, and pan-fry it whole, almost like a massive vegetarian schnitzel.
I've heard it's delicious.
And while the stipe is far too fibrous and tough to chew, foragers don't throw it away. They dry the hollow stems and grind them into a fine powder to use as an umami-rich seasoning or stock base.
But hunting for Macrolepiota procera in the wild is fraught with severe risks that extend far beyond heavy metals. The genus Chlorophyllum sits right next door on the phylogenetic tree.
The lookalikes.
Exactly. It shares the exact same meadow habitats, and it is full of highly toxic lookalikes that can easily deceive an amateur forager.
Right, the visual mimicry is terrifying. The most notorious offender is Chlorophyllum molybdites. It goes by the common name, the false parasol, or even more descriptively, the vomiter.
Very apt name.
It grows in the exact same grassy fields, it reaches a similar towering stature, and it has very similar concentric scales on its cap.
And its nickname is entirely earned. Ingestion of Chlorophyllum molybdites causes severe, violent gastrointestinal distress, extreme cramping, and severe dehydration. It is consistently ranked as one of the most frequent causes of acute mushroom poisoning in North America.
So how do you tell them apart?
The absolutely critical diagnostic difference, the only way to be absolutely certain, is the spore print.
Okay.
Macrolepiota procera, the true parasol, drops pure white spores. Chlorophyllum molybdites drop spores that are distinctly grayish-green.
Which means you literally have to take the mushroom home, cut off the cap, set it on paper, and wait hours to see what color dust falls out before you can safely eat it.
Yes.
And it's not the only threat. There's also Chlorophyllum rhacodes, the shaggy parasol, which looks incredibly similar, and also causes gastric upset in a large percentage of the population. You have to verify the white spore print, the snakeskin pattern on the stipe, and the freely movable enzymatic ring. It is high-stakes foraging.
Given the intense culinary demand, the immunological benefits, the high levels of 5-HTP, and the severe risks of wild foraging, both from lookalikes and heavy metal bioaccumulation, the obvious industrial solution is to cultivate it indoors.
Just farm it.
Right. We farm button mushrooms, shiitakes, and oysters in massive, sterile, climate-controlled facilities. Cultivating the parasol would completely eliminate the heavy metal risk and the misidentification risk.
Right. If we can grow a portobello in a bag of manure, why can't we easily farm the parasol?
Well, the research papers looking at cultivation basically read like a chronicle of scientific frustration.
It's a nightmare for them. Trying to domesticate the parasol is an absolute nightmare for mycologists. It is incredibly recalcitrant.
It refuses to conform to standard agricultural models. To cultivate a standard agaricus button mushroom, you essentially need composted straw, manure, and a dark room. The organism is highly adaptable.
But the parasol isn't.
No, Macrolepiota procera demands exact, almost impossibly narrow environmental parameters. First, there is the pH. Most commercially farmed fungi prefer a slightly acidic environment around pH 5.5 or 6 because acidity suppresses competitive bacterial growth. The parasol absolutely demands a strictly neutral pH of 7.0 to properly colonize a substrate.
And it is incredibly picky about its carbon sources, too. You can't just toss it in a bag of sterilized hardwood sawdust like you would an oyster mushroom.
No, I won't eat that.
It's a specialized saprotroph. Studies show it requires highly specific, nitrogen-rich substrates to thrive. The mycelium aggressively demands substrates supplemented with specific amino acids, like glycine, and very specific complex sugars, like maltose. If you don't feed it exactly what it wants, the mycelial growth just stalls out.
But the true hurdle is what mycologists call the fruiting barrier. Even if a laboratory perfectly balances the pH to 7.0 and formulates the perfect high-nitrogen glycine maltose substrate, and the mycelium successfully colonizes the entire bag,
It still doesn't work.
it simply refuses to fruit. The organism is alive, it is healthy, it is metabolizing, but it will not produce a mushroom.
It's like having a bioreactor full of healthy code, but it refuses to run the executable file.
That is an excellent analogy. To trigger the fruiting sequence, the organism requires a highly specific, complex sequence of environmental shocks that simulate the exact onset of European autumn.
It needs seasons.
It needs a massive thermal shock, where the ambient temperature drops sharply from a warm vegetative state down to exactly 16 to 20 degrees Celsius. Simultaneously, it requires a specific calibrated drop in ambient humidity. And even if a lab perfectly simulates this microclimate shift, the primordia, the beta mushrooms, often just abort and die.
Which brings us to the most fascinating theory in the recent cultivation literature. The reason it won't fruit in a 30-day crop cycle in a plastic bag is because it might actually be a perennial fruiter.
Yes. This fundamentally changes how we view its life cycle. Unlike a fast-fruiting oyster mushroom, the parasol may require a massive, undisturbed, fully integrated mycelial network that has been colonizing and establishing its territory in the soil for 6 to 12 continuous months.
It needs time.
It needs that vast established architecture and the massive energy reserves it holds before it possesses the metabolic capacity and the complex environmental signaling required to push up a 40-centimeter water-dense fruiting body.
So you can't just treat it like an agricultural crop. You can't just feed it and put it in a box. It refuses to be reduced to a sterile industrial process. It demands an entire complex ecological operating system.
Exactly.
It needs its bacterial partners, its specific nitrogen ratios, its seasonal thermal shocks, and a year of undisturbed underground growth just to perform.
And synthesizing all of that brings our entire deep dive full circle. This wild, untamable recalcitrance is essential to its biological identity. An organism that is sophisticated enough to engineer localized convective wind currents, recruit and manage protective colonies of Cannabicillus validus, selectively hyper-accumulate specific environmental isotopes, synthesize anti-tumor beta-glucans, and manufacture massive quantities of mammalian neurotransmitters like serotonin precursors to protect itself from UV radiation.
That's a lot for one organism.
Right, an organism of that immense complexity cannot be simplified into a bag of sawdust on a warehouse shelf. Its biological brilliance is inextricably, fundamentally linked to the staggering complexity of the wild meadow ecosystem it evolved to dominate.
Wow, that is the perfect encapsulation of what we've been uncovering. We have covered a massive amount of incredibly dense science today.
We really have.
Let's run through a quick recap of the journey. The parasol mushroom, Macrolepiota procera, begins as a tightly sealed drumstick, utilizing hydraulic turgor pressure to violently shatter its cuticle and expand into a 40-centimeter tall biomechanical masterpiece. It relies on a hollow, wind-resistant skyscraper stem and a central structural umbo to stay upright.
And once elevated above the boundary layer, it utilizes evaporative cooling from its massive gill surface to generate localized, continuous convective downdrafts, literally manufacturing its own microweather to fling its spores into the turbulent winds.
When those spores land, they build a massive centuries-old underground network that acts as the soil's heavy metal filter, violently sucking up mercury, silver, cadmium, and even radioactive polonium-210.
That same advancing saprotrophic network recruits highly specific bacteria to mine minerals and defend its borders, leaving behind massive nitrogen-rich fairy rings and hydrophobic dead zones that terrified medieval Europe and inspired centuries of enduring folklore about dancing elves, fiery dragons, and malevolent curses.
And on top of all of that sheer ecological dominance, while it's sponging up lethal toxins, it is simultaneously synthesizing complex MP-CPS beta-glucans to prime the human immune system against tumors, and pumping out massive quantities of 5-HTP to create the chemical building blocks of human happiness.
Unbelievable.
It is an absolute biochemical paradox, a master of fluid dynamics, and a species that completely refuses to be tamed by modern agricultural science.
It is undeniably the king of the meadows. It is a biological sentinel that forces us to entirely redefine our baseline assumptions of what a simple fungus is capable of executing.
Exactly. So the next time you are walking through a field and you see a perfect geometric ring of towering, scalar umbrellas standing silently in the grass, remember what you are actually looking at.
It's not just a mushroom.
No, you aren't just looking at a fungus. You are looking at the exhaust vents of a massive, ancient, highly communicative underground chemical factory. You are looking at an organism that is actively manipulating the atmosphere and rewriting the chemistry of the Earth simultaneously.
It is a profound reminder of the invisible, immense complexity humming just beneath the surface of the natural world.
Which leaves us with a final provocative thought to ponder. If fungi like Macrolepiota procera are actively managing complex transactional economies with specific soil bacteria, if they are physically manipulating thermodynamic principles to alter fluid dynamics and disperse their spores against the wind, and if they are synthesizing highly complex mammalian neurotransmitters like serotonin and melatonin to chemically defend themselves against environmental stress,
are we missing something?
exactly. Are we fundamentally underestimating their level of environmental sensing and biological intelligence? It makes you wonder what else they are doing right beneath our feet, pulling the strings of the global ecosystem completely unseen and unmeasured. Something to think about the next time you take a walk in the woods.